All right, so I have a video for section 13.2, day 2. We're going to take a look at integrating vector valued functions. Rotate my screen. Okay. Let's see, make sure the ink works here. Smiley face with a vector on top. Always good. Okay. Integrals of vector functions. So very similar to what you did in Calc 1 and in Calc 2. You have definite integrals and you have indefinite integrals. When you take the integral of a vector valued function, what it amounts to is really taking the integral of each component function. Now, just a little recap in terms of what the definite integral is, because it applies in a very similar way to vectors. The definite integral of a continuous vector function or vector valued function r of t works very similar to how you have done it for functions of a single variable. Remember, definite integrals are the ones that have bounds. So just as a reminder, that looks something like this: integral from a to b of f of t dt. Okay, difference being now that's only going to be one of our components. You're going to have something that's either two-dimensional or three-dimensional. So every single component is going to be an integral itself. In Calc 1, what you did is you looked at how a definite integral is really the sum of a bunch of infinite rectangles, right? So when we do it for a vector valued function, we take the limit as n approaches infinity of the sum of r of t sub I star times delta t. Let's do a quick recap on what some of these pieces are from what you would have done last year. Last year, you may have called this delta x. Think of this as your delta x. This was the base of your rectangle. R of t sub I star, we'll talk about t sub I star in a minute. This was the height of your rectangle. Okay. Base times height gives you area. So altogether, this is basically adding up the areas of all of the rectangles. Okay. T sub I star, you talked about a couple different methods last year for approximating definite integrals. You used left endpoints, you used right endpoints, and you used midpoints to approximate definite integrals. So this is really, it could be the left endpoint, it could be the right endpoint, it could be the midpoint, or it can be really any point inside the partition that you're picking. So I'm just going to put any value in the interval of the partition that you choose. Most famous types to pick would be a left endpoint, a right endpoint, or a midpoint. But it doesn't have to be. It could be some point that's 2/3 of the way to the end of the interval, or 1/3 of the way from the start of the interval. Okay. But we're still basically adding up bases and heights. The difference is we have to do it 3 times. We have to do it for the x component of the vector valued function, we have to do it for the y component of the vector valued function, and we also have to do it for the z component. Okay. Remember what the limit in front means? This means we're letting the number of rectangles grow to infinity. And the size of the rectangle should be getting thinner and thinner and thinner as you increase the amount of rectangles. And eventually when you do that, is you let the number of rectangles grow to infinity. This was the symbol that you used last year for the definite integral. Okay. So this is really the result that we get. Summary, this box. You can evaluate the integral of any vector valued function by integrating each component function. Do it once for x, do it once for y, do it once for z. Okay. And so we can extend the fundamental theorem of calculus to continuous vector functions as follows. The integral from a to b of some vector valued function r of t is equal to some antiderivative vector valued function. If you remember last year, I'm going to put off to the side what you would have written. You guys learned that a to b of f of x dx is some antiderivative capital F of x evaluated from a to b. And we evaluate the top bound first, we evaluate the bottom bound second, and then we take the difference of those two quantities. This was the fundamental theorem of calculus, one part of it, for a single function. Now we're doing something similar, but we're going to have to do it multiple times because we have a vector valued function. So we use capital R, which is a vector, for the antiderivative of that space curve little r. If you have a definite integral with bounds, you would evaluate using the fundamental theorem in a very similar way. You would plug in the top bound, you would plug in the bottom bound, and you would subtract. However, just to clarify, this will result in a vector, whereas this from last year would have resulted in a scalar. So that's one of the main differences. We can also do indefinite integrals, antiderivatives, in which case if I integrated r of t dt, I would still get my antiderivative space curve, r of t, but I wouldn't have bounds attached to it anymore. And if you remember from last year, when you do this with definite integrals or with indefinite integrals, the integral of f of x dx was equal to capital F of x, that antiderivative. There was always a plus c involved as part of your antiderivative. When we do this with space curves, because we're dealing with vectors, that constant really ends up turning into a constant vector. So it's going to be a vector of constants for each piece. So that's important. I'm going to make sure I highlight when we use our notation here. Okay, so that's a lot of the background that goes into it. Let's solve a few problems just so you can see how it works, and you'll get a lot more practice with this on your packet and on the WebAssign. I tried to pick a mixture of definite integrals and indefinite integrals. So for example 1, we have the curve r of t equals t squared I plus e to the tj minus 2 times cosine of pi tk. We want to evaluate the definite integral from 0 to 1 of r of t dt. Okay. So really, we're just going to go component by component. I'm going to write it out. 0 to 1, r of t dt. You can use bracket notation or you can use IJK notation. That's up to you. I think I'm going to try to do it both ways in certain problems just so you can see what's going on. I'm going to choose IJK for this one. So what we're going to do is we're going to take the integral of the first component, the x component, 0 to 1, t squared dt. So I take the definite integral of my x plus, I'm going to take the definite integral from 0 to 1 of e to the t dt, j, plus I'm going to take the definite integral from 0 to 1 of negative 2 cosine of pi t, don't forget your dt. Okay, so just component by component, I'm passing the operator through. I'm passing through the definite integral to each of the component functions, x, y, and z. And then I'm going to evaluate each one of them. So in the first one, come over here for some space. Antiderivative would be 1/3 t cubed from 0 to 1. I. Second one would be e to the t from 0 to 1. J. For the last one, if you want to do some scratch work off to the side and use a u-substitution, you could. Your u in this case would be pi times t. If you go through the u-substitution, though, what's going to happen is you're going to end up dividing out by pi. So we're going to end up with negative 2 over pi sine pi t. Antiderivative of negative cosine would be negative sine pi t from 0 to 1. Okay. And we get, this would be 1/3 minus 0 times I, plus this would be e to the first minus e to the 0 times j. And this one, let's be careful with, we're going to get negative 2 over pi times the sine of pi. Sine of pi is 0, so this is 0. Plugging in 0, we get negative 2 over pi times the sine of 0, which is also 0. So the k component of your vector drops out. I'm going to come up here just to write my answer. Whoop. So my final result would be 1/3 I. E to the first minus e to the 0 would be e minus 1. Make sure you put that in parentheses since that whole thing is getting multiplied by j. And that would be the result of my definite integral. Again, it's not a scalar, it's a vector because you're integrating a vector valued function. You could also write this in component form. This would be 1/3 e minus 1, and our k component was 0. Okay, so that takes care of the first one. Let's do an antiderivative Let's do one that doesn't have bounds. So we've got a definite integral this time. I think notationally for this one, just to make things a little simpler, I'm going to label these 1, 2, and 3 and just do them separately. But what we're going to do is we're going to take the integral of the function next to I, we're going to take the integral of the function next to j, and we're going to take the integral of the function next to k, and we're going to express them as a vector. So let's do number 1. Integral of 2 cosine t dt. Thinking of a function that has a derivative of cosine would be sine, so this would be 2 sine of t. Now remember, we're going to have to do this 3 times, and at the very end, we're going to have to include a plus c, but that c is going to be a vector, and it's going to be made up of 3 components. A constant from the first vector, a constant from the second, a constant from the first component, a constant from the second component, and a constant from the third component. And so that's going to create a vector of 3 constants. So I'm going to call the first one that goes with the first component function c1. For number 2, I've got cosine squared t sine t dt. Maybe for yourself, pause me for a minute and see if you can think about what technique you would need to evaluate this integral. This doesn't have a very clean antiderivative. You're not going to be able to do this directly. Okay, unpause. This is a u-substitution. So I'm going to write it off to the side. In this case, the inner function would be cosine, so I'm going to let my u be cosine t. My du would be negative sine t dt, which means that my negative du would be sine t dt. So this turns into integral, negative integral, pull the negative out front, u squared du. So I get negative 1/3 u cubed plus c2. The problem started with t's, so let's make sure we go back and plug in cosine t for u. So this would be negative 1/3 cosine cubed t plus c2. And last but not least, I'm going to come up here. Number 3, last one we have. Nice easy finish on this one. That was the hard workout. Now we get the easy cool down. The integral of 2t dt, we just use the reverse power rule here. Increase the power by 1 and divide by the new power. So this would be 2 t squared over 2, which would be t squared. Plus, don't forget your constant. I'm going to call it c3. So putting it all together, our result, I'm going to pick a new color. I'm bored with the same colors. Let's do blue. This thing right here, I'm going to say equals. First component was this. So we're going to get 2 sine ti. Second component gave us this piece minus 1/3 cosine cubed t j. Running out of space, I'm going to go to the next line. Third component gave us t squared plus t squared k. And last but not least, all 3 of these constants are going to be placed into one constant vector, which we're going to call c, which is made up of c1, c2, and c3. Not to be confused with C-3PO from Star Wars. If you have no idea what I'm talking about, don't worry. That would be my antiderivative. And I'm going to say it again. Don't forget the plus c. I'm sure you heard that a lot last year. Okay, last one. You can also solve these problems if they give you an initial condition. So in other words, you can solve for C1, C2, and C3. So let's end with one of those. Find the original space curve r of t, given that the tangent vector is given by t I e to the tj plus t e to the tk, given that the initial value r of 0 is I plus j plus k. So in other words, they're telling you an initial condition. I'm just going to write that here. And I like to work with things in component form sometimes, so I'm going to use 1, 1, 1 just to clarify for us. Okay, what do we got? We need r of t, so we're going to have to go from r prime back to r. So think about that. What that means is that r is an antiderivative of r prime. So r of t would be the indefinite integral of r prime t dt. I'm going to use component functions for this one. Makes it a little bit easier. I think I'm going to work my way down this way. Okay, so I'm integrating. What's r prime? T e to the t, t e to the t. Don't forget your dt notation is just as important as it was last year. Well, two of those look fairly simple to do, and one of them looks maybe a little bit more work. You decide which one that is. I'm thinking that one. Okay, so let's maybe do that one off to the side. We're going to have to integrate each piece. The third one looks like the most work. This one is going to either require you to use integration by parts, or anytime you have an algebraic function attached to an exponential, a trig function, you can use tabular integration, but there has to be an algebraic function as one of the components, which we have. T is attached to an exponential function. T is an algebraic function. So I'm not going to do it both ways in the video, but I'm going to pick the shorter one. I think tabular would be the way to go for this one. So let's do a little tabular integration off to the side. Your u in this case, if you remember your best choice of u, whenever you're using tabular or integration by parts, you can use the acronym LIPIT. This would be your best choice of u all the way to your worst choice of u. Stands for logarithms, inverse trig functions like arctan, arcsine, arccosine, polynomials like t, t squared, t cubed. Those are all fairly good choices of u. Exponentials and trig functions are awful choices of u. Those are better choices for dv. So my u in this case, I'm going to let be t. That's an algebraic function. I've got a polynomial. And my dv in this case is going to be what's left over, which would be my e to the t. The exponential would be a poor choice of u. Okay. The way tabular works, just as a reminder, the left column where we have u equals t, we are going to take derivatives of that function until we get to 0. So in this column, you are taking derivatives. So if I take the derivative of t, I get 1. If I take the derivative of 1, I get 0. In the right column, I'll do this in green, I am taking antiderivatives, so I am integrating. If I integrate e to the t is its own antiderivative. Therefore, if I do it again, I still get e to the t. And then I pair them up diagonally. These two are going to get multiplied together. These two are going to get multiplied together. It always alternates sign. Positive product, negative product, positive product, negative product. We only have to do 2 products in this one because once we do that, we get to the 0 in the third round. So putting it together, I would get t e to the t minus 1 times e to the t. So my antiderivative here would be integral of t e to the t dt would be t e to the t minus e to the t. And that's the third component, so I am going to put a little plus C3 just so that we're being formal about it. It's going to end up going in a vector in a minute. Okay, now we can go back to the original problem. So I get r prime of t equals integrating the first piece. Integral of t would be 1/2 t squared, comma, integral of e to the t would be e to the t, and we did this one off to the side. This would be t e to the t minus e to the t. And I'm actually going to put the C3 in its own vector now because it's going to become part of the actual constant vector that we have to attach onto the end. So this gives us r of t equals 1/2 t squared, e to the t, t e to the t minus e to the t, lots of e to the t's. Plus, okay, 3 components means constant 1, constant 2, constant 3. I'm going to put a little dividing line here so we don't get confused. This was only the third component off to the side. Okay, now we want to evaluate, we got to look at the initial condition. We are plugging in for t the value 0. So we are going to put r of 0, which comes out to 1, 1, 1. I plus j plus k, this would be 1, 1, 1 when t is equal to 0. Okay, so this thing I'm putting in right here, that's r of 0. And in for t, therefore, I'm going to have to put in 0. So I'm going to get 0. E to the 0 would be 1. 0 times e to the 0 would be 0 minus e to the 0. 0 minus 1 would be -1 plus C1, C2, C3. And again, I'm going one step at a time just for the purposes of you seeing it for the first time. You might be way ahead of me right now and already adding things together component by component. That's good. Move me along if you're feeling like you're getting it. So I'm going to get component by component 0. I'm going to add these two. 0 plus C1 would be C1. I'm going to add the second two. This would give me C2 plus 1. I'm going to add the third ones, C3 minus 1. And I'm going to need a new page because I'm running out of space. Insert. Oh, hang on. Add a page. Let's continue it over here. Okay, so let me just write down what we had so I don't lose it. Where were we? Okay, 1, 1, 1 equals draw. I'm going to write that line again so I have it. 1, 1, 1 equals C1, C2 plus 1, C3 minus 1. And then what's nice is we can equate the left and right hand sides. So C1 has to equal 1. C2 plus 1 has to equal 1. And C3 minus 1 has to equal 1. So right away I get C1 for free. C2 plus 1 equals 1 means that C2 has to equal 0. C3 minus 1 equals 1 means that C3 has to equal 2 if I add 1 to both sides. So now I've solved for my constant vector, right? This was C1, C2, C3. I already found all three constants, so I get 1, 0, 2 is my constant vector. So to finish the problem, they asked for the original space curve. What was r of t? Well, before we had t squared over 2 plus 1 e to the t, e to the t minus e to the t plus the constant vector, but we just found the constant vector. That's this. This is c. And last but not least, I can combine the components together. I can put the first components together, the second components together, and the third components together. So I would get, oh, sorry, one quick little error that I have here. I'm jumping ahead too far. This first piece right here didn't have the plus 1 originally. It was just 1/2 t squared. We're going to add the 1 in a minute. So this is going to be 1/2 t squared plus 1. Second piece is going to be e to the t plus 0, so that will stay e to the t. And last but not least, this piece plus 2 would be t e to the t minus e to the t plus 2. Make sure all my pieces look good. That is our space curve. If you feel like graphing that for fun, that's a good exercise for yourself. Okay. Homework-wise, you've got WebAssign, you've got Packet. If you have questions, bring them to class next week before we quiz, and I'm happy to answer anything that you're stuck on. Hey, happy mathing.